In this video, we will see some basic sorting algorithms, namely selection sort, insertion sort, and bubble sort. Basically, we assume that a set of unordered elements is given to us in an array and we need to put these elements in increasing or decreasing order in the same array. We will study how each algorithm works and analyze its time complexity. The first sorting technique we are going to discuss is selection sort. Carefully look into the animation. As we can see, an iterative process is followed, and after every iteration, the array is divided into two halves, in which the left part is sorted and the right part is unsorted. Gradually, the sorted array increases in size and the unsorted array reduces in size. After the first iteration, say iteration 0, the zeroth index contains the correct element. After the second iteration, say iteration 1, the first index contains the correct element. Thus, after the first two iterations, that is iteration 0 and 1, the zeroth and first element are in sorted order whereas elements 2 to n-1 are unsorted. Let us understand the working of the algorithm. At every iteration, we scan the array's unsorted part to find the minimum element. Now, after iteration I, the array indices 0 to I are sorted and indices I plus 1 to n-1 are unsorted. So, at iteration I plus 1, we scan the array elements from index I plus 1 to n-1 to find the minimum element. This is just a linear search problem on an array of size n-e-m. Thus, every iteration of the selection sort requires another inner iteration to find out the minimum element in the unsorted part of the array. The time required for linear search is theta of n if n is the size of the array. After finding the minimum element, we just swap the elements stored in index I and the index that contains the minimum element. This process continues n-1 times, and after this the first n-1 elements, that is the elements stored at indices 0 to n-2 get sorted. Note that the last remaining element is the largest element of the array, which is already in its proper position. See the algorithm. The outer loop runs n times, and for each iteration of the outer loop, the inner loop runs less than or equal to n times. So, the time complexity of the selection sort is order of n square. You can also think in the following way. At iteration 0, we need to scan n elements to find the minimum one, which takes order of n time. At iteration 1, we need to scan n-1 elements, which takes order of n-1 time. At the final iteration, we need to scan just two elements, which takes order of 2 time. So total time taken to sort the array is order of n plus order of n-1 plus all the terms up to order of 2. If we sum up n, n-1, n-2, up to 2, we get the dominant term as n square. So, the time complexity of the selection sort is order of n square. Let us take a deeper look into the time complexity analysis of selection sort in the next slide. Next, we try to write down the recurrence relation for selection sort. If T(n) is the time required to sort the given array of size n, we scan through all the elements to find the minimum one, which takes theta of n time. Then we swap this minimum element with the first element of the unsorted subarray, which takes constant time or theta of 1 time. After this, we need to repeat the process for a smaller unsorted subarray of size n-1, which will take time t n-1. Hence, the recurrence relation can be written as T(n) equals T n-1 plus theta of n plus theta of 1. Ignoring the constants, and writing theta of n as some constant c multiplied by n, we can write the same recurrence relation as T(n) equals T n-1 plus Cn. On solving this recurrence relation, we get Tn equals order of n square. Note that for selection sort there is no best or worst case. All cases are equally good or bad.
The next sorting algorithm we are going to study is insertion sort. Carefully look into the animation. Here also, at every iteration we divide the array into two smaller subarrays, out of which the left part is sorted and the right part is unsorted. But the process is different from the selection sort. At iteration 0, we pick the element at array index 1 and compare it with A0. If A1 is less than A0, we store the value of A1 in some temporary variable, assign the value of A0 to A1, and finally assign the old value of A1 stored in the temporary variable to A0. Now, array indices 0 and 1 are put in sorted order. At iteration 1, we have to sort the array indices from 0 to 2. For this, we pick up the element at array index 2 and compare it with A1. If A2 is more than A1, then no further comparisons are needed with the subarray elements to the left of A1, since this subarray is already sorted in ascending order. However, if A2 is less than A1, then we have to compare A2 with A0 as well. If A2 is more than A0, then we know the correct location for A2 after sorting is index 1. So we store A2 in a temporary variable, shift A1 right, that is, assign the value of A1 to A2 and finally put the value stored in the temporary variable to A1. If A2 is less than A0, we need to shift both A0 and A1 one index right, that is, assign the value of A1 to A2, then assign A0 to A1, and finally put the value stored in the temporary variable to A0. This process repeats till we reach the last index of the array. During implementation, at iteration I, we can perform the series of comparisons of the target element I plus 1 with the elements in its left subarray to find its desired position. Say this location is array index j. Now, all elements from A, j to A, I need to be shifted one place to the right. Finally, A, j will be assigned the value of the target. Insertion sort worst case situation arises when the given array is sorted in descending order. This is because at each iteration the target element needs to be compared with all elements to its left and all elements to its left need to be shifted one index to the right. Consider the worst case scenario. If the time taken to sort the entire array is Tn, then Tn is equal to Tn-1 plus C into n-1. Here Tn-1 is the time to sort the first n-1 elements and n-1 is the number of comparisons required to insert the nth element into its correct position. We also need n-1 right shifts. The total time taken for comparison and shifting of the n-1 elements is written as C multiplied by n-1. We can solve the recurrence relation to get order of n square. The best case situation for insertion sort arises if the array is already sorted in ascending order. Note that, in this case, only one comparison is needed at each iteration and no right shifts are required. One comparison can be done in constant time. Hence, the recurrence relation for the best case of insertion sort is given by Tn is equal to Tn-1 plus C. On solving this recurrence relation, we get order of n. On average, insertion sort takes order of n square time.
Bubble sort is another simple sorting algorithm that works by repeatedly swapping the adjacent elements if they are in descending order. It also divides the array into two parts. As per the animation, the right subarray is sorted and the left subarray is unsorted. We make multiple passes through the array and in each pass, we shift the largest element to the farthest right of the sorted subarray. Gradually the size of the sorted subarray increases and the size of the unsorted subarray reduces. In the first pass, the largest element is shifted to the last array index, while in the second pass, the second largest element is shifted to the last but one array index. Let us understand how the algorithm works. In the first pass, we compare A0 with A1 and the larger of the two will be placed in A1, while the smaller one will be placed in A0. Then A1 is compared with A2, and the larger of the two is placed in A2, while the smaller one in A1. The process repeats until we compare the last pair of elements, that is an-2 and an-1, and perform the necessary swapping. This completes the first pass. Note that, after completion of the first pass, the largest array element is positioned in the last index, that is, an-1. Now, we freeze the last element and make a second pass through the array from index 0 to n-2. This positions the second largest array element at the array index, n-2. We repeat the passes through the unsorted part of the array while gradually reducing the unsorted array size. Finally, we are left with an unsorted array with one element, which is the minimum element of the given array that is already placed in its correct position, that is index 0. At this stage, we terminate the algorithm. If T(n) is the time taken to sort the n-element array, then in the first pass we make n-1 comparisons and swappings, whenever required. This takes order of n time, and the first pass places the largest element to the farthest right of the array. Next, we need to repeat this process on an array of size n-1. Thus, the recurrence relation for bubble sort is T(n) is equal to T(n-1) plus C(n-1), which gives order of n square time. For the algorithm, we discussed, there are no specific best or worst cases. It takes order of n square time always. However, we can keep an extra condition check after each pass which can make the algorithm more efficient. Basically, we can check if no swappings were required in a particular pass. If this condition is true, then there is no need for subsequent passes, since no passes are required only if the array elements are in sorted order. If we put this extra condition, we can have a best case for bubble sort when the given array elements are in sorted order. Just after one pass which takes order of n time, we can terminate the process since no swappings are required in the first pass.
Thank you.